In this video, we're going to be taking a look at the different types of intermolecular forces in some detail. So let's start off with our dipole-dipole forces. Dipole-dipole forces exist between two or more polar molecules, and they do need to be polar. And the way dipole-dipole forces work is that it's an attraction between the electronegative end of one molecule and the electropositive end of another. In other words, if you look at HCl, HCl is a polar molecule, and the Cl is more electronegative, so the Cl side has a partial negative, and the H side has a partial positive. And so the partial negative Cl over here is attracted to the partial positive H of, or partial H of another HCl molecule, a separate one. So this here would be the dipole-dipole interaction. Or here we have H2S. There's a dipole that forms on here. We have a partial negative S and a partial positive H. The partial positive H is attracted to the partial negative H of another molecule. And so this is a dipole-dipole force. It's very weak, but it's still an attraction between them nonetheless. And so you need to have two or more polar molecules for this to happen. So here we have polar molecule, another polar molecule, and the partial negative is attracted to the partial positive. Again, these are partial charges because they're not full charges. They're covalent bonds, not full transfers of electrons. The other thing to realize is that the more polar the substance is, the stronger the dipole-dipole force is. So for example, if the bond between HCl is more polar than the bond between HS, this is going to be a stronger dipole-dipole force. So a dipole-dipole means an attraction between dipoles of two separate molecules. And again, two polar molecules. Now, there's another type of dipole-dipole. It's actually a stronger type. It's called a hydrogen bond. And the hydrogen bond happens between polar molecules, still polar, but those polar molecules need to have either an HF group, an NH group, or an OH group. So we like to remember that trick by saying hydrogen just wants to have fun. So if you have polar molecule, let's say like water, two polar molecules here, these both have OHs. The partial positive of H is attracted to the partial negative of the O from another water molecule. This is a dipole-dipole, but a special type. It's a hydrogen bond dipole-dipole because it has an OH group. The NH, HF, and OH are very polar groups. So that's why the dipoles from them, the dipole-dipole interactions from them are stronger than just a regular dipole from, let's say, an HCl or an HS type of group, or a CCl type of group as well. So if you see HF, NH, OH, and it's a polar molecule, then it's going to have a dipole-dipole that's actually a specific type called the hydrogen bond, which again is stronger. So here we have some hydrogen bond between two HF molecules. Here we have hydrogen bond between two ammonia, NH3, because it has the NH group. And so these are very, very strong dipole-dipole interactions. And actually, it's a hydrogen bond that gives water such a high boiling point. Generally, bigger molecules will have a higher boiling point. But water is such a small molecule and it has a pretty high boiling point for its size. And it's really because the hydrogen bond is a pretty strong intermolecular force that you need to break. So here's a connection that we can make for biology for some of you biologists out there, or if you plan on taking biology in grade 12 or in your future studies. This is your DNA molecule, part of a DNA molecule. And the DNA molecule is made up of two strands. This is a strand over here, and over here, this is another strand. So think of it like two strips. And you'll notice that here there's these dotted lines, and those dotted lines are what hold the two strands together. And those are actually hydrogen bonds, right? You can see the NH groups there, for example. So hydrogen bonds exist there. And when you want to copy your DNA, like you're in interphase, mitosis, all that stuff there, you have to replicate DNA. Well, you have to break the hydrogen bonds to open up to separate the strands and read the letters so you can start copying them. And that's just a connection of some forces that exist within our own biology, within living things. All these forces we're seeing, they apply to chemistry in test tubes, but also to chemistry within the bodies, within living things. So we get to another force here called the London dispersion force. Sometimes they abbreviate it LDF. So all molecules and all atoms and all substances, they have London dispersion forces. Think of this as the default. It's the force that everything has. It's the base level. Whether it's polar or nonpolar or whatever, everything has London dispersion forces. But for nonpolar molecules, London dispersion force is the only force that they have. Remember that for a dipole-dipole interaction or hydrogen bond, you need to have, well, partial charges. You need to have polar molecules. Nonpolar molecules don't have those partial charges. So they can't do dipole-dipole, and they can't do hydrogen bonding. The only thing they can do is something called the London dispersion force. And so how does that work? Let's take a look at the molecule F2. This is F2. This is another F2. And there's an attraction between them, even though there's no partial charges. What I want you to get is that there's still electrons here. They're sharing electrons. So the electrons in a bond or within a substance are always moving around. And as they move around from time to time, sometimes there'll be more here than, let's say, over here. So as they move around, there'll be a temporary moment where one side has a partial negative and one side is a partial positive. And so, for example, that's what happened here. For a temporary moment, a moment in time, a dipole was created, and that's called an instantaneous dipole. Because just because the electrons are moving, it's nothing permanent. In the other examples, these are permanent dipoles; they're always there. But here we have a temporary dipole that develops just because the electrons are moving around, and that happens in another molecule as well. And when that happens, these molecules can now be attracted to each other. It's a very weak force. It's actually the weakest intermolecular force of all, but it's still there nonetheless. So, for example, here we have Cl2. It's nonpolar. Cl2, nonpolar. But there is a London dispersion force here because the electrons move around. And for example, if the electrons moved here for a few seconds, this was slightly positive. And over here, if the electrons moved here for a few seconds, this was slightly negative. And they were attracted to each other. So we say that they're instantaneous dipole moments. They're very, very weak, and they're not permanent. They're temporary. Sometimes what can happen is a dipole can be created in a molecule just for a moment and cause another dipole in another molecule just by attracting electrons in certain directions. And that's what happens here. So they're temporary dipole moments that exist in all substances, but they're the only substance in nonpolar forces. So for example, if we look at H2O. H2O has a few different forces in it. There's the London dispersion force. That's one of them, but it's very weak. And then there's also the hydrogen bonding. HF has London dispersion forces. I didn't draw them in here, but they exist there. But it also has the hydrogen bonding. Whereas something like F2 is nonpolar, so it has only London dispersion force and no dipole-dipole or hydrogen bonding. And now we get to the last intermolecular force that we study in grade 11, which is called the ion dipole force. We'll see more detail of this later on, but it's essentially a force between a full ion and a dipole. So for the dipole-dipole force, it was just a force between partial charges, a partial negative, partial positive. But for the ion dipole, it's a force between a full ion, like a full charge, and then a partial charge. So for example, here we have a full negative charge, and here we have a partial positive charge. Here we have a full positive charge, and then a partial negative charge. This is actually what you see when you're dissolving salt in water. Here's the water molecules, and you can see the partial negative oxygens are surrounding and attracted to the positive sodium ion. And likewise, the partial positive hydrogens would be surrounding the partial negative ions, the chloride. So when you dissolve salt, that's basically what happens. Water surrounds the different ions. The partial negative parts of water surround the positive ion of your salt, and the partial positive part of your water surround the negative ion of your salt. And so to really understand this in more detail, I do want you to watch a video on ion dipole forces here, and also how dissolving happens, because that'll be very important going forward to explain that dissolving process. And we'll see more of this in the next lesson. So here's our summary of the atomic forces. So if you have a molecular compound, you can have intermolecular forces. And those intermolecular forces can be London dispersion forces, dipole-dipole forces, or hydrogen bond forces. And the intramolecular forces for molecular compounds are covalent forces, covalent bonds. So they can be single bonds, double bonds, or triple bonds. And generally, triple bonds are stronger than double, which are stronger than single. And over here you can see the strength of the different intermolecular forces that exist in the molecular compound. So dispersion is the weakest. You can see that because the energy required to break them is not very high. Dipole-dipole follows that. And then hydrogen bonding is a stronger dipole-dipole. And then the ion dipole is a stronger one of all of these. So strongest one here, and you can see examples on how to draw them. If I were you, I would also practice, if I give you a molecule, can you draw an example of that force happening between the molecule? And we'll do some of that in the next video as well. For ionic compounds, the forces that exist between them are the ionic bonds or electrostatic forces, basically just full-on charge interactions. So we're going to learn how to identify what types of forces exist in each molecule in the next video. But to finish off this video, let's go and fill in some blanks. So our dipole-dipole interaction is when you have a partial positive charge of one molecule attracted to a partial negative charge of the other molecule. And this really happens between two or more polar molecules, because you need those partial charges there. And generally, the more polar the bond is within those polar molecules, the stronger that dipole-dipole interaction. And then we also have a hydrogen bond, which is a very strong version of a dipole-dipole interaction. It's still weaker than intramolecular, like covalent, but it's stronger than a regular dipole-dipole. And that happens when you have F, O, or N, when you have those special groups, the NH groups, OH groups, and HF groups, because they're very electronegative and polar bonds, and they lead to stronger dipole-dipole interactions. Really, it's just a very, very strong intermolecular force, and it's actually stronger than the dipole-dipole. And when I say very, very strong, I mean very strong compared to the other intermolecular forces. It's still weak on average compared to the covalent bonds or ionic bonds. But the hydrogen bond is the reason why it has such a high boiling point. Water has such a high boiling point of 100 degrees Celsius. For example, there's some molecules, like I'm going to draw a really big one here. So CH3, CH2, CH2, 1, 2, 3, 4, 5, 6. Let's do up to 7. So this molecule here, I don't remember the exact boiling point, but let's say it's around 70-ish degrees Celsius. This is a really big molecule. This molecule here is non-polar. And I know that because it's only CH bonds, and CH bonds are non-polar. So this is a non-polar molecule. Now water is a very small bond, but it has 100 degrees Celsius boiling point. A very small molecule, I should say, sorry. But it has a very high boiling point compared to this huge molecule here. And that's interesting. And let's see why that is. So if we look at this molecule, it's non-polar. So the only force it can have is a London dispersion force. It's one of the weakest molecular interactions. So it's a weak intermolecular force, and it's actually the only force that exists in non-polar molecules. Everything has them, but it's the only force in non-polar, because non-polar don't have any partial charges. And again, the reason that those form is because you have these temporary or instantaneous dipole moments that form because the electrons move around. So they're temporary. They're not permanent. So for example, and one important thing about this is that the bigger that your compound is, the stronger the London forces are. That's because if you have a bigger compound, you have more atoms, you have more electrons, and with more electrons moving around, you can have more of those temporary charges forming. So bigger compound with more atoms and more electrons, and generally just bigger, more massive, a higher mass, means that you're going to have more London dispersion forces. So if we look at this molecule here, it's a very big molecule. So it's going to have a fairly high, boiling point-ish. It's not super high, but it's 70 degrees Celsius. Okay, to get to that, you need to be at 70 degrees Celsius to evaporate this. But water is much smaller, but still has a higher boiling point. So why is that? Well, this has way more LDF. It actually only has LDF. And water does have LDF too, but not a lot because it's so small. There's not a lot of electrons in that molecule. But what gives it this high boiling point? Well, you guessed it. It's polar, and it has a much stronger force in it, the hydrogen bond force. And so it takes more energy to disrupt the hydrogen bond force than it does to disrupt the LDF found within that big molecule. So a lot of these forces have to do with their physical properties, and this is kind of a little taste of how those physical properties are affected by those forces. And one last example here. So you'll see it in more detail in a future lesson, but we have I2 here, Br2 here, Cl2 here, and F2. I2 is actually solid at room temperature. Bromine is liquid at room temperature, and these ones are gas. So these are all non-polar. I know they're non-polar because it's simply a bond between the same atoms. So the electronegativity difference is going to be 0. So that's like pure nonpolar. So now, that being said, the only force that can exist between all these diatomics here is really just the LDF. So of all these, which one do you think would have the most LDF? Look at the state. Which one's harder to evaporate or melt? Right, I2 is solid at room temperature, whereas Br2 is liquid. So this one didn't melt yet at room temperature, so there's probably a lot of LDF preventing the particles from moving away far enough to melt. Br2 is liquid, so it's probably a little bit less LDF than I2, and then these ones are gases. So these ones here have weaker LDF than both Br2 and I2. And the reason for that is if you look at this, it has to do with the size. Iodine is very massive. If you look at the periodic table, let's go find it in our handout here. If you look at the periodic table, iodine is a big atom. Look at the mass over here, 126.9, and it has 53 electrons. Bromine, 79.9, 35 electrons. Cl, 35.45, 17 electrons. And then fluorine's even smaller. Now, I know we have Br2, sorry, we have I2, Br2, so double the electrons for each, but still, compared to the others, I2 is very massive, has more electrons, and so therefore has more LDF than the rest of them. And it's really LDF that explains the difference in their boiling point and their states at room temperature, because there's no other forces in them. They're non-polar. The only force they have is the LDF. And the last force we saw was the ion dipole. There's a video here to give you some more instructions on that and more details on it, but it's an attractive force between an actual ion, so a full ion, so a cation or anion, and the molecule that has a dipole. So in other words, you have to have a polar molecule. So for example, it could be a full negative ion and a partial positive charge, or a full positive ion and a partial negative charge. And that's what you would see in dissolving. The partial negative oxygen of waters are surrounding the full sodium ion if we're dissolving salt. So when you dissolve salt, you take some solid salt, put it in water, and then you just separate the ions. You're not decomposing the compound. You're just separating the ion because the water comes in between them. But they're still technically together. They're just separated by water molecules now. This is a physical process. Dissolving is physical. If dissolving was chemical, it would look like this. You'd have NaCl solid. You'd produce solid sodium, which is sodium metal that reacts with water and basically explodes. And you'd also produce sodium chloride, which is, just regular chlorine gas, which is toxic and would not be good for you to breathe in. So this is not what's happening when you dissolve. The water is just separating the ions and surrounding them because they're forming ion dipole interactions. So the oxygen will be attracted to the partial oxygen will be attracted to the positive sodium ion, and then the partial positive hydrogen would be attracted to the negative chloride ion, the full ion there. So these are ion dipole interactions that we're seeing here, and that's how dissolving happens. So do watch the video that's in the little slide deck there that goes over the ion dipole in a bit more detail. And so in the next video, we'll see how to identify elements, or how to identify the different forces in various compounds and substances.